Hi, this is Jim. If you shoot 22 rifles seriously, you inevitably end up in this problem where your favorite batch of ammo is starting to get down to your last brick and you got to buy some more. And inevitably, even if you're lucky enough you can buy the same make of ammo, you're never going to find the same batch 2 times in a row. So you're into this problem of testing out ammo to see what shoots well in your gun. And there's 2 ways you can basically approach this. One is to go to a testing center, which is indoors and air conditioned, and your gun is in a vise and really high-tech equipment. So you'll get as best possible data doing that. But the problem for me is the nearest testing center is a couple states away, so it's a major undertaking to go do that. And so the fallback is to do my own testing, which is what most of us do. But now you're outdoors with wind and temperature changes and whatnot. And so, the question I had for myself was, well, how good a job can I do testing my own ammo? And specifically, how many shots do I have to take in order to distinguish between 2 different batches of ammo? And so this video is sort of broken up into 2 parts. I'm going to take you to the answer pretty quickly, which was a little bit discouraging, but I'll show you what I came up with. And then the second half, I'll go more step by step and show you the way I approached the problem, how I collected the data, and I learned a few things doing that, actually. Okay, so let's get started. I think you're going to see a lot of targets here, and I've decided to make the targets in units of MOA, minutes of angle, just because it's independent of distance and whether you're shooting metric or US units. Now, if you want to think about it in old money, the blue circle on the target is 1 MOA, which is about 1 inch at 100 yards, so give you a context. But, since it's an angle, it really doesn't matter what distance you're shooting. The other thing I'm going to be using to begin with is a nominal 1 MOA rifle, which is a rifle which, if you shoot it a whole bunch of times, 95% of the bullets will fall within the 1 MOA circle. You're still going to have some scatter 5% outside of it, but basically it's a pretty good rifle. And so we'll use that as a benchmark, and then I'll look at a half MOA rifle a little bit later. Now, to sort of give you a feel for what you're up against when you do testing, let's look at some groups. And the first group here is 3-shot groups. And if you knew nothing else, imagine you had to decide how much money you'd like to pay for the lot on the left versus the lot on the right, because it's obviously a lot better. The joke here is these are actually the same lot of ammo. This is a simulated 50 3-shot targets, and there's going to be a best one and a worst one, and all the rest will be in between. And what I'm showing here is the best target and the worst target given on 1 MOA rifle. And the problem with just 3 shots is once in a while you'll get lucky and you'll get 3 really good ones, and some of the time you'll get really unlucky and you'll get those outliers. And so there's like more than a factor of 5 in spread here, even though it's exactly the same ammo. So, 3 shots is not enough. Okay, the next is 5-shot groups. Again, I've shot, in practice or in theory, 50 targets, and this is the best and the worst. And it's still very similar. You're getting pretty big difference, but you notice the ratio, the spread ratio between the best and worst is down to about 3 to 1 now. So as we're adding more bullets, what's happening is the probability of getting all good ones or all bad ones goes down. You start getting a more representative sample. And it continues with 10-shot groups. It's still quite a big difference, but it's getting a little bit better. And by 20-shot groups, you're starting to see, okay, there's definitely a difference between the worst and the best, but it's a much smaller difference than we saw, of course, with smaller groups. And so that's sort of the driving force between thinking about, how many shots do I have to take? So here's the basic answer from the analysis, and I'm showing, this is, to begin with, this one MOA rifle, and the top columns are basically how confident I am in the result. So 90% confidence means I'm pretty sure, but there's a 10% chance I'm wrong. And that's probably good enough for what we're doing. We don't need to be super confident. But just for completeness, I'm showing 95% confidence and 99% confidence, which is, you're absolutely certain at that point. And then over on the left, I'm looking at how much difference is the spread of the ammo I'm bringing in to look at versus the ammo I'm shooting already. And so to begin with, let's look at a 2 MOA difference. Well, we started out with a 1 MOA group, and now we've gone up to a 2 MOA spread on top of that. That's like you go out and buy a bucket of crummy ammo at the local gun shop, and you're comparing that to Ely or Lapua. It's not going to take you very many shots to figure out that this stuff is really bad. So, it says you're theoretically in 7 shots, you're already 90% confident that that stuff's no good. Okay, that was sort of ridiculous, but let's go down to a 1 MOA difference. So this is something which on average has got twice the spread of the one that we've already got. And it's a bit alarming. It's already taking 16 shots to differentiate the ammo we've got with the ammo we're testing. And it gets, of course, worse at 0.5 MOA, just half again the spread. It's taking 40 shots at 90% confidence, and you really can't shoot enough bullets to get any much past that. So that's pretty depressing. It's taking a lot of bullets, and we're not really able to distinguish a lot. But let's look at what happens if our starting point is we've already done a lot of ammo testing and we've got a pretty good gun. Now we're going to look at a half MOA rifle. And this is a really good gun. For example, when I did testing with my Voodoo using Ely Team, 160 shots, my equivalent MOA outside, temperature changes and all that, was 0.6 MOA. So this is better than that. So it's a good gun. And the numbers come down quite a bit. So, looking at the 1 MOA difference, it's only taking 8 shots. Now we can clearly distinguish the 0.5 MOA difference in 16 shots. But then we have trouble getting past that because there's enough scatter, even with a half MOA gun, that even if you shoot infinite numbers of bullets, you can't really refine the last bit. And that's just because there's some scatter. And so you can't be completely confident that one batch is better or worse than the other unless the differences are significant. Anyway, I found that a little bit depressing. It sort of does explain why there's a good market for these test centers. But if you're interested, let me take you through the logic on how I came up with these numbers. And the real key to this thing is I had to check, is the ammo and gun I'm shooting random? Because if it's random, it's going to be very predictable in aggregate on the average, not individual shots, but when you look at large number of shots, then it starts becoming very predictable. And so in order to test that, I shot 160 rounds at 100 yards using my Voodoo apparition and Ely Team. The winds were pretty light, 3 to 5 knots. One thing I didn't handle very well was I started in the morning and the temperatures gradually rose, so that had some effect on the results. Explain that in a second. Now here's a little diagram of the quote-unquote the normal distribution. If something is truly random, then it's predictable in average, and it will tend to data if you add up how much is at different, off to the left or off to the right or off up or off down. Those differences will tend to follow this bell curve. And you're probably familiar with SD, standard deviation, if you use a chronograph. A chronograph is just a measurement of how fat that spread is, where one standard deviation plus or minus will give you 68% of the data, and two standard deviations will give you 95% of the data, and so on. But again, they're assuming with the chronograph that the data is random, which as far as I can tell is a pretty good assumption for velocities. Okay, so how to collect the data. If I shot 160 rounds into one target, it would be obliterated. So what I did was I came up with a couple of these targets, 80 on a sheet, and on these intersections I basically numbered them. And so on every intersection I shot one bullet, and I also measured the chronograph for that shot. And then when I got home, I could measure how much it was away from the center by vertically and horizontally. And if you were to combine all of those shots and make the bullets really tiny so you can see the holes, this is what the target would have looked like. And you can see there's a couple of outliers, but basically the data is falling well within the 1 MOA. And so, it's approximately a 0.6 MOA at 95% confidence. So that's pretty good. Now, the next thing to do is to check, is this data really random? And so looking at the data from the bottom, if you bin up how many are off to the left, a little bit more, and so on, and you add those up, you get the little blue dots on the right, which shows you the comparison of the normal distribution if it was completely random and these shots. And this was sort of ridiculously good fit. I mean, it's obviously very close to random. Now that was horizontally. On the vertical axis, it was a little more scatter in the data. It still looks pretty darn random. But I think one of the mistakes I made in doing this is the temperature was gradually rising, and I didn't compensate for that. If I had to do it again, I'd set a target at 50 for zeroing, and then maybe every 20 shots while I'm shooting at 100 for data, go back and just double check my zero. I think that would have helped. So if you look at what was happening to the muzzle velocity over that period of 160 shots, it was gradually going up. Not a lot, but it was enough to affect the data. And just sort of a sidebar, but it's interesting if you plot how far off the bullet was up or down versus the velocity, you get this scatter diagram. And as you'd expect, as the velocity goes up, it tends to make the bullets go high, and vice versa. When the velocity is low, the bullets tend to be low. And if you push a pencil on the ballistics, it basically works out that the line through here is exactly what you'd expect from the difference in time it takes a slow bullet versus a fast bullet to get to the target, and the difference in drop. The interesting thing is how much scatter there is. I had it in my mind that the vertical scatter was just due to changes in velocity. And that's true for the extreme cases, like the very worst vertical error is the fastest bullet, and some of the very worst vertical errors are some of the slowest bullets. But the majority of the scatter in here is not related to the velocity. It's due to some other influences, wind, I don't know what. And so if you work it out, the math, only 30% of the scatter is attributable to the velocity. The other 70% of that vertical scatter is some other random cause that I don't know about. Interesting. Not something I can do a lot about, but it just tells you, a lot of people have made the observation that they get a batch which has a good SD from the chronograph, but it actually doesn't shoot as well as something that has a higher SD. And I think this sort of explains that. The SD is a meaningful number. It tells you something about the consistency, but don't expect it to be an absolute predictor of the amount of vertical scatter, because there's other factors involved. Okay, so anyway, I've convinced myself that I've got a a random distribution. The bullets are flying around randomly, which is great because now they're predictable. And so one thing I can do with this is make simulations. So on the left, that's the actual scatter of the bullets that I measured. And on the right is a simulation with the same standard deviation. It's the same 0.6 MOA. And you can see, they're very, very similar. Each of the shots landed in a different spot, but this random approach predicts how the shots are going to fall very well. And of course, every time I run it, I'm going to get a different group on the right. Sometimes they look a little better, sometimes they look a little worse, but they all have the same statistics. So that's what gave me the confidence. Okay, I can push a pencil on this. Now, how to do the actual calculations if you want to do them for yourself. What we're looking at, we don't care about the zero of each different group of bullets because we can just adjust our sight. So basically, all the shots are going to have the same zero, regardless of what kind of ammo we're testing. What we care about is the scatter. And so if you think about it in terms of distribution, if our base ammo is the black curve here, what we're looking for is better ammo, which would have the red curve. And what we're trying to avoid is like the green curve, where the ammo has much more scatter. But they all have the same mean. And statistically, this is just when you want to figure out whether you can distinguish two populations based on how much they're spread. There's a standard statistical test called the F-test that does that for you. The F-test is just the ratio of the standard deviation, the SD of batch 1 versus the SD of batch 2. That's all there is to it. And so, when I set a 1 MOA gun with 95%, you remember 95% is actually 2 standard deviations. So a 1 MOA gun with 95% confidence is a 0.5 MOA at 1 standard deviation. So let's take a case where I said the bad ammo, or the ammo I'm testing, is 1 MOA worse, 1 MOA higher standard deviation than the ammo I'm starting with. And so the F-test is going to be 1.5 divided by half, or 3. And I'm making the assumption that we're going to do the same number of shots for the good ammo as for the bad ammo, or the test ammo. For the base ammo as the test ammo. One other little weirdness, when you look up F values, it doesn't say the number of shots. It says degrees of freedom, and that's just the number of shots minus 1. Okay, so if you go online or in a textbook, you can look up F distribution. Here's a table at 95% confidence. And what you're trying to do in this case is find the number 3, where the number of shots for both the test ammo and the base ammo are the same. It turns out to be 6 shot, or actually it turns out to be degrees of freedom of 6, which add 1 means it takes 7 shots to make that distinction. So that's where those tables of numbers came from. Okay, enough of that. Conclusions. I think if you look at those tables, it seems like 20 shots, 15 to 20 is a good compromise. If you're shooting less than that, there's pretty high probability that you can get fooled once in a while by, all good or all bad shots. If you're shooting more than that, it seems like you just sort of run into this very uphill battle that you can shoot 60 or 100 and really not improve your confidence that much. So I ended up deciding for myself 20 is probably a good reason, a good number. The other thing that comes out of here is, at least in this scenario, a lot of times you're really not going to be able to tell the difference between groups. There's just enough randomness in the base data that it obscures small differences in the test data. And that's a fact of life. Another thing that I had, I think, a misconception that then when I bought a box of ammo, there was the good stuff, and then there were occasionally these bad bullets in there that went flying. And if I could only pull those bullets out, I'd have good ammo. And that's a nice fantasy, but I think a better way to think of it is that every box of ammo has some distribution, some bell curve. The good stuff, the bell curve is really small. It still has tails. You're still going to have, no matter how small your group is, you're still going to have bullets that are occasionally outside of that group. They make up that last 5%. That's just the way random things go. But the tighter that group is, the happier we're going to be. And so that's what we're shooting for. And I guess my final comment is that doing all this makes me appreciate why people go to test centers. I mean, it's really a way to get much finer detail. You're going to end up with the same issues of distributions, but of course, the smaller you can make the starting point by controlling all these variables that you can control, the better distinction you're going to be able to make between one group and another. So I just wish there was a test center closer to me. Okay, thanks very much. I hope you enjoyed this. Bye.